I'm Trevor Cox, and I suppose I'm normally in charge, but it's very much a group effort of the Cadenza project, which is using challenges to try and improve the processing of music on hearing aids and consumer devices. And the idea of this webinar today is to try and introduce the latest challenges and allow you a chance to ask questions. So that's the kind of plan of attack for today. I'll keep it fairly brief, but I'll just say what Cadenza is, and then Alinka Greasley is going to come in and talk a bit about why these two tasks are important for people with hearing loss and why we need to tackle them. I will then go in and give an overview of the tasks, and at that point we'll have a Q&A. And if you have questions, you go along, feel free to use the chat. You could unmute and ask questions, bear in mind it'll be recorded, or just raise a hand or wait for the Q&A bit. So if you've got things you need answering, please just let us know. We'll then have a tutorial which will show us about how to use the baseline software and other things that Gerardo is going to give to us as well, and then we'll have another Q&A at the end. So that's the plan of attack. So this is a 4.5-year project. We're going to run 3 sets of challenges, and this is the second challenges. And we've run challenges called CAD1, and we also run a challenge for the last ICASP. And if you're interested, actually, I just literally a day ago uploaded a paper we've submitted to a journal on these challenges if you want to look at the past one. But the whole idea of the project is to basically get people to think about people who have different hearing, who have hearing loss, when they're looking at music processing. Alinka.
Okay, thank you, Trevor. So yeah, just a little bit of a background to the sort of problems that we're trying to address. We know that there's a really high prevalence of hearing loss in society. So the World Health Organization estimate that 1.5 billion people are currently living with hearing loss. So that's around 20%, and this is set to rise. Now, there's a number of different sort of perceptual and psychological and social consequences of hearing loss. Perhaps the most well documented is problems with speech perception, particularly in noisy environments. And this can lead to communication difficulties, which in turn can lead to social isolation and also loneliness. So if hearing loss goes untreated, then it can also lead to cognitive decline as well. Obviously, this is a project about music, so we're interested in sort of what are the consequences of hearing loss for music. And Brian Moore did a paper in the Journal of Audio Engineering Society back in 2016 that really sort of outlined what all of these consequences were. So to give you some example, if you've got hearing loss when you're listening to music, you'll have if you've got hearing loss, you'll have an elevated threshold. So that's difficulties with audibility. You might struggle to hear quiet music, and generally the pattern of loss is that the high frequencies will you lose high frequencies first, so there'll be some difficulties with hearing out high frequencies. Also reduced frequency selectivity of the cochlea, so this affects auditory discrimination, so our ability to hear out pitches and melodies. And loudness recruitment is another consequence. So this is wherein the difference between a sound being audible and unpleasantly loud is actually reduced for those with hearing loss. So this can impact music perception in a number of different ways. Now, hearing aids are the primary technology to treat hearing loss. So they're increasingly sophisticated for speech perception and facilitating verbal communication. And there's a lot of evidence that they improve quality of life because they enable a person with hearing loss to engage more fully in their everyday environments. Now, hearing aids are primarily designed for speech perception and not music perception. So while they provide some benefit for music, so they help users to hear out different musical elements, there's also quite a bit of evidence that the experience of music through hearing aids can be poor. So there are reports of music being distorted or hearing aid users experiencing feedback. and also poor sound quality. So there are some difficulties that are related to the hearing loss itself, but actually there's evidence that the hearing aids can make that listening more difficult when it comes to music. So the most frequently experienced problems are then around pitch perception difficulties. So this is sort of being able to hear out melodies and identify different instruments. Hearing aid users report problems with hearing the lyrics in music, and obviously this is something that we're concentrating on in this next challenge. Often complaints of a sort of lack of clarity and sound blending or blurring, or just in general the sound quality being poor, with people experiencing sort of feedback and distortion. Hearing aid users also report difficulties with dynamics and volume change, and also more problems in live settings than in pre-recorded settings. So what we're doing with this next challenge is actually we're focusing on two areas. We're focusing on, first of all, source separation. Now we know this is a key part of musical appreciation, so the ability to pick out an oboe melody when in an orchestra, or to pick out the tenor in a choir singing. So you know it's a really key part of the enjoyment of music. But we know that hearing impaired listeners experience problems in identifying instruments and also picking out, for example, those melodic lines. And this has been reported to be particularly difficult with music that has a great complexity and lots of layering of instruments and voices, which you can see here in these quotes. And some recent research work on musical scene analysis has actually shown that picking out instruments is harder with an increased number of instruments in the mix, and also harder with the more hearing loss that you have as well. So we really wanted to sort of tap into this. And if you sorry, I've got somebody tapping on my door at the moment, which is very distracting. There are approaches that have been used to try and improve the experience for people with hearing loss. Actually, quite a lot of the work has focused on CI users, and this has shown some of the potential of remixing. So, for example, experiments have shown that for cochlear implant users, they prefer lead vocals to be enhanced in relation to other instruments, and also prefer a sort of broader spatial distribution of instruments when listening to classical music. What we don't know so much about is, this approach hasn't really been used with people with hearing aids. There is one study that's been carried out by Benjamin and Siedenberg in Oldenburg, which has looked at the potential of remixing for hearing aid users. They explored a number of mixing transforms for listeners using popular music. So they had kind of change various parameters, lead to accompaniment ratio, spectral balance, and EQ transform. And what they found was that hearing impaired listeners preferred an elevated lead to accompaniment ratio, and also music that was higher in spectral sparsity. But we've so that's about how the instruments are sort of sitting in the low, sort of how spread out the instruments are in a mix, a sort of undermix or overmix. But there are no studies of specifically remixing classical music for hearing aid users, which is what we're focusing on here. And one of the reasons for this is because a lot of the population that we work with, the hearing aid user populations, tend to be older, and there was a general preference for classical music among this group. So that's why we chose to focus on this for the first task. And then the second task is around lyrics intelligibility. Now, I did some work a long time ago. It was sort of when I was first doing my doctoral work. I was looking at music appreciation and the characteristics of music that are important for people, and consistently lyrics are a really key part of people's musical enjoyment, hearing out the lyrics and understanding the lyrics in music. But it is a common problem for those with hearing loss. So I've included a couple of examples from some of our participants here, just saying, you know, if I can't hear the lyrics, there's little enjoyment in listening. You know, just saying it's all a mush, I can't hear it. Yeah, sorry, I have a very, very insistent person knocking on my door. Trevor, could I just ask you just to
Yeah, I'll take over.
pick this up? Sorry, I'm very sorry about this. Yeah,
It's like the good old days of COVID, isn't it? Where people would interrupt people. Anyway, I'll carry on. So yeah, so lyrics is kind of really a key thing that our panel want us to kind of tackle. So a link had basically got to the end of a talk almost anyway. So I'm now going to sort of go into the challenge itself and look at what we're proposing to do. So just to give you some key dates, well, obviously the challenge went live over the summer. We'll be releasing the evaluation data in December, and the actual deadline is in 17th of January for people to submit the audio for their systems, and also to submit a technical report so we can tell what you've done and see if you met the rules. We then got listening panel work to be done. So we'll have evaluation of one of the tasks for our listening panel, more of that at the moment. That will run in February to May. And then we're actually going to be running our workshop as part of the International Congress on Acoustics, Acoustic Society of America meeting, which is in New Orleans in May next year. There's going to be a special session that we've got arranged in that conference. There's a deadline for abstracts in early January, which kind of fits quite well with our submission deadline. And there was a proceedings paper. I don't know the deadline, but the proceedings for ICAs and ASAs are quite brief. So it's not going to be too onerous, but you can always write more. They always want you to write more. But historically, those were quite brief. So that's the kind of time scales we're kind of working to. So let me take the tasks. I seem to have numbered the other way around to a linker, so apologies. So I'm going to do with task 1, lyric intelligibility. I guess we've got to start with the definition here. I think we probably intuitively know what it was, but our hearing loss panel said how clearly and effortlessly the words in the music can be heard is our kind of definition of lyric intelligibility that we'll be working off. So we've given you a baseline system, and Gerardo's going to demonstrate some of these systems later, but I'm just going to give you an overview in a sort of schematic way. So basically, what we have is we have a scene generator which will generate music and some metadata we'll talk about. Because this is about processing music for someone hearing loss, we're also going to have listeners which will be randomly selected, and they'll have hearing characteristics. Those are audiograms. I'll talk a bit about those later on. And then that's fed to a system which is meant to make the music better for someone with a hearing loss. So the music comes in, it's processed, and then it's better for the person with hearing loss. So when you're working on the challenge, it's this pinky music enhancer. There's the block that you're going to be working on. This schematic is showing the objective evaluation we're doing. So we'll talk about this in a bit more detail about HAAQI later on, but HAAQI is a quality measure, and Whisper is Whisper ASR. So that's doing an intelligibility measure, which we combine to do a score. And we'll talk about why there's 2 measures and a balanced score to be done later on. What's not shown on this panel as well is we'll also be sending your samples, your enhanced music samples, over to a listening panel who will do listening tests. Well, they'll be asked to score the equality and the intelligibility, and we'll do a sort of similar balance score to work out what the end result is. So you can imagine someone with a hearing aid like I am has got the hearing aids out, but got the headphones on, and what you're trying to do is make a headphone processing. So what's played off the headphone sounds better for them, and that's your music enhancer block. Maybe think of it like that. So I'm going to take these different blocks and look at the different things, starting with the music. In terms of the music and the training data set, because our baseline does this by demixing, remixing, and because this could be tackled by that method, and we expect quite a lot of people to do that, we've taken Muse DB18HQ because it's the kind of benchmark for demixing tasks. So we're using the train split for that. We've given you some other databases there listed that you can also use. Now, if you want to go beyond those, we need you to contact us and check that it's okay. I mean, generally, we know in these sort of tasks that the more data you have, the better you'll do. And hence, we don't want people using private data sets and just getting advantage by having access to vast amounts of data. If you want to use a public data set, but we've missed, we're happy to add it to the challenge, but you need to talk to us first of all. So you've got this normal train split, which if you've done any demixing challenges before, you'll know. For those who don't know the database, I suppose we hadn't said this at the top, this is sort of pop rock music. And what MuseDB18HQ gives you, why we're using it here, is it has the tracks already split. So we can have the reference of the kind of what is the pure correct vocals because they were recorded separately. You're very welcome to use all standard augmentation techniques. In fact, things like randomizing the stems is pretty standard in this kind of area. And I think one thing we just want to highlight is be careful if you're using pre-trained models. Again, these need to be public and they need to be published and they should be developed on public data sets. We had an entry last year who used some pre-trained models which had used stuff which didn't meet the rules and they had to retrain their models. So just be careful. Again, if you've got any doubt, just contact us and say, I'm thinking of doing this. Is that okay within the rules? We're here to help. In terms of evaluation, which as I say we'll formally release in December time, we've got some Jamendo lyrics and MuseDB and 18HQ lyrics as well. Just the important point here, this is not here to refine your system. It's not here for development. This is purely, you'll get these, you'll run the thing through the system, and then you'll send us the stuff for evaluation. So it's not for you to use for development. So looking at that diagram, that's the music. We've also got the listeners. And if many of you will be familiar, for those who aren't, what we measure the listeners is their threshold, called their audiograms in their left and right ear. And this is typically the way hearing audiograms are shown. So you've got frequency up here and hearing loss going down here. And if you're young and you're somewhere up here, and if you're like me, you're somewhere down here. As you get older, and as you get older, you tend to lose the high frequencies. And we've given 3 databases. We've got training set, a validation set, and evaluation set, which we'll send to you nearer the time. And what they will be is left and right levels, the points on these graphs, essentially. And I should say, I'm going to, as I go through, some of the stuff I'm talking here about lyric intelligibility is the same for the other task, which is the rebalancing classical music. So this is one where the listener metadata is exactly the same. So I won't talk about it again a bit later on. What I would say is if you're not familiar with some of this hearing loss, we have quite a lot of materials on the website. So if you go to Cadenza and look, there's learning resources which actually explain what audiograms are and how they're measured to help you sort of kind of understand this area if it's new to you. So going back to the schematic, we've now got the scene generator and we've now got the listener. Let's move on to the enhancer and other parts of this this process. So in the enhancer, what we have for the baseline is actually we have a demix remix process. So we separate this out into, I'll show a diagram in a moment, but lyrics and other instruments. And then a very simple way of improving intelligibility is make the vocals a bit louder. So there's some, you could obviously do something much more sophisticated than that if you wanted, but if you've demixed it, then it allows you to sort of play around with intelligibility in different ways by playing around with the vocals and the other tracks. But although we've kind of highlighted that and our baseline does that, please don't feel that's the only way you could do it. So if you've got other sort of end-to-end approaches that you want to do, that's absolutely fine. But there's also lots of techniques in speech enhancement. This is basically a speech enhancement problem, except for the words are sung and the statistics of the signals are a bit different. So you could think about learning a non-binary mask or something like that and using that in a sort of speech enhancement way. All methods and ones we haven't thought of are very, very welcome. And then we get into evaluation on the right-hand side here. And these are the blocks in the baseline that you're not altering, we're providing. And as I said, there's also a listening panel as well, not shown here. And so I forgot, I clicked back by accident. So this is the baseline enhancer, just to give you a sense. I need to show you this to talk about a couple of things. So we've got the music to enhance. We demix it into vocals and accompaniment. We just change things by using amplification. And there's this alpha value that I'll explain in more, which actually drives the amplification, how much the vocals are turned up, essentially. We then just add those signals together, we remix them to stereo, And the other thing I wanted to just, well, reason I need to show this is an amplification stage. And that amplification stage is dealing with the fact that you've lost your high frequencies and they need amplifying. So this is where the hearing aid part kind of comes in. So this first block is about enhancing the signal, but this bit is about dealing with hearing loss. And that pops your enhanced signal. So you could change all of this or part of this. So for example, you could leave the amplification block with our default one and just concentrate on this part if you want. You could use our default demix and maybe do something more clever with this remixing process. You could just play around with the amplification process if you want. All of those are allowable, or you could change the whole thing as you kind of feel fit. So as I said, there's this alpha value, which is giving you the different gains that in our case we apply, and essentially, but it's using the evaluation to balance between intelligibility and quality. So it's a value, if we look at the final score, we're going to score for intelligibility, we're going to score for quality, whether that's an objective score or a listening panel score. And we're going to use this formulation here to give the final score for each sample. And we'll give you a range of alpha values to use when we kind of ask you to evaluate data. So if we give you alpha equals 1, we're saying basically everything is about intelligibility. If we give you alpha equals 0, we're saying everything is about quality. And so your systems need to be able to not just improve the intelligibility, they need to do it in kind of varying degrees as well. So that's what our alpha is exploring. Now, there probably, if we talk to people with hearing loss, there is some balance they want between intelligibility and quality, but we don't know what that is at the moment. So we're asking you to make a system where that sort of kind of can be explored, because we know it will probably vary with listener preference. It'll probably vary with hearing loss, and it will probably vary with the music people are listening to. So we can't at this point, unfortunately, know, but when we've done a listening test, we'll have a lot more information about where that balance should lie. So we want to explore the balance and have a systems which can explore that balance, because then in the listening test we'll learn actually what do people really want. So the evaluation, you saw the blocks here. Let's do the objective first of all. So the intelligibility one is essentially we're using the Whisper ASR algorithm, which is now the Clarity project showed kind of worked. It works really quite well for speech intelligibility, and actually it also works quite well for lyric intelligibility as well. So what we do is we take that enhanced audio your music enhancer has generated, and first of all we have to pass it for a hearing loss model, because we need to simulate the effect for the listener. So we have a hearing loss model you see in the PyClarity Git. Then we pass it for the Whisper algorithm, which then produces a text transcript, and we look at the percentage of words that are correct for that. So that's the kind of process for doing intelligibility. For quality, we're using this hearing aid audio quality index, which James Cates and others developed. This is an intrusive metric that uses a reference, so it's doing a comparison. So in my schematica, you had a music reference and you had the process music. They're doing a comparison, a correlation. We are averaging the left and right signals, so we do it separately for left and right, and we can use that in task 2 as well. Listening panel, we haven't actually finally done the last design, so I can't show it to you at the moment, but basically they'll be scoring intelligibility and quality separately, and then again using this combined scoring to bring the two things together. So if you want to learn more about things like the HAAQI measure, sorry, the HAAQI measure where you're kind of using, then we have a nice sort of kind of talk by James Cates, who kind of developed this with others, about these kind of metrics he developed. There's a variety of ones. This is a speech one, but there's also, as you see down here, a hearing aid audio quality index. So there's a speech and audio ones, and he does a talk about it and explains it. And this is an extract from our website showing some of the sort of kind of stuff we use to help people engage with the material. So if we go back to the baseline enhancer, the bit I haven't really talked about, so we talked about alpha, which we're using just to determine levels, but you could do something else with. I want to just mention this amplification and what that is. So if you remember hearing loss, most of our hearing losses have kind of this characteristic where we're losing the high frequencies. So we need something to amplify the high frequencies. In the past, we've used NALR, a linear amplification. Now we're moving to something slightly more sophisticated. So we're simulating what you would get if you were to go into a clinic and get a hearing aid. So that's a non-linear amplification using dynamic range compression. So it breaks up into frequency ranges and applies different dynamic range compressions depending on the frequency range and also your loss in each of those frequency ranges. As I said, you could make a better one, or you could use the default one if you want. Just one sort of kind of thing to highlight it's because it's got a non-linear compression, then you need to make sure the levels going into this compressor are roughly right, otherwise it won't perform quite as you want. You don't have to get it exactly right. So make sure you've got the levels roughly the same as we do in the baseline. And the other thing to say is HAAQI is a comparison. It's this kind of comparing a reference to the baseline. So the amplification we use in the HAAQI before we actually calculate HAAQI is the same as we use in the as we use in the baseline enhancer. They match, and that's important as well. Now you might decide that you want to use a different amplifier. If you do that, because the reference in HAAQI is using this amplification scheme, and if you use a different amplification scheme, they'll differ. Your HAAQI scores might go down, but you might do that because you want the listening panel to do better, because you know you can do better than HAAQI in your metrics, and that's fine. And we're happy to see two systems. We see this seen this before, where someone says, "Here's my system where I optimized it for HAAQI, and here's one where actually I think this will do better in the listening panel," and that's fine as well if you want to do. And again, this is the same for the next task I'm going to talk about as well. So that's the kind of general sort of kind of setup, and later on we'll kind of Gerardo will go into a bit more of the details of this kind of the actual software which runs this. So the final thing which is mentioned, I think, before I look at task 2 is causality. So if we're looking on a hearing aid, so we've got a device which is working real time, we want causal processing systems. So that's really useful. But also, you could imagine a lot of things we listen to are recorded. You know, we get out Spotify or something and listen to something which is pre-recorded. So there's no reason why non-causal signal processing isn't useful as well. And so we're happy to see both causal and non-causal systems being entered. It's got different kind of uses, but they're both useful. We would imagine that causal is going to be harder than non-causal because you have less information to work on. Now, if you decide to make a causal system, I think it's really important to say that it's really easy to do something which is non-causal processing by accident within either, say, a DNN or within, say, normalizing signals. Gerardo wrote a page about causality, which you'll see on our website. It's worth reading that because it kind of highlights the places where you might accidentally do non-causal processing. It also talks about what the limit is on causal. You know, how much information can you use in the future, because you use a little bit in the future. So don't mind if it's causal or non-causal, but if you're doing causal, just be careful that it truly is. The other thing I would say is we don't have a limitation on model size. So there's no sort of computational limit. You can make this as big or huge as you, and millions of kind of things if you want. So that's sort of task 1, and I thought it might be a good idea just to ask before I launch into task 2 whether there's any questions on this particular part that we've kind of got through so far. And I'll take a quick drink and pause for a second. Feel free to raise your hand. You could unmute, or you could put something in the chat. Howard, you've got your hand up. You could feel free to unmute and chat if that's where you want to do it. You'd need to unmute though, Howard. You're muted. You're just muted at the moment, Howard. Can't hear you. And I can't unmute you. You actually. Well, while Howard wrestles teams, you could type the question in the chat if you want, Howard, instead. Which I know is annoying. Well, there will be other chances to ask questions, Howard. I know that must be very frustrating, but feel free to put it in the chat. We could pick up in a moment. As there's no other questions on that task so far, I'll go and describe the second task, and then we'll have a Q&A after that. So start thinking of your questions as well. Task 2 is about rebalancing. Trevor, thank you. Sorry.
There is a question.
Thank you very much. Now, the pronunciation of your name is interesting. Andre, potentially. Feel free to unmute and just ask us a question. You're currently muted.
Hi, Andre. Andre here from AudioShake. You can hear me right? I was wondering if it's possible to use lyrics datasets for training for these tasks? Like, for example, the MuseDB18 lyrics extension, or possibly DALI, or datasets like this.
So you just got to be careful. Gerardo probably knows the databases better, so you might want to comment here that we are an evaluation set using some MuseDB lyrics. So just be careful you don't use that part of Muse 18DB, but the other bits are fine to use. I don't know the DALI one myself. If you could, maybe put in the chat the details of it. We're more than welcome to go and have a look at it and see. You know, as long as it's public and available, we're happy to sort of kind of make it available to more teams. Our principle here is that if people want to use stuff, we want to make sure that everyone knows about it, so we don't end up with people just using very large amounts of data that people weren't aware of. So you can put it in the chat and we'll have a look, or you could drop us an email and we'll have a look at that as well.
Right.
Is that okay?
And then I was wondering also, yeah, great, thank you. I was wondering also about the pre-trained models. So it seemed, according to the rules, using pre-trained models trained on public data would be okay. So I guess, well, you're using Whisper in the evaluation. I guess it would not be okay to use it during training because it's trained on who knows what. But there is, am I correct? It would be not okay to use Whisper, or?
Yeah, so I guess, yeah, to be clear, what we're talking about is actually the part of the music enhancer bit. So if you're using Whisper as an evaluation tool to drive an optimization process, that's fine, because that's part of our evaluation block that we have provided.
Right, we were thinking, what if it's used in some part of the training, actually?
In what you mean, beyond it just being an evaluation tool to give an intelligibility score?
Yes.
Leave that with us, and we'll have a think, unless someone else from the team wants to comment.
Okay. Then there are also other. There is this other model called Awesome, or OWSM, which is a open source Whisper style model, which is trained only on public data. So if not Whisper, perhaps that one would be okay. I can send the link as well.
Yes, I could comment on that. I think, yeah, that would be a very good idea. So I think that the Awesome models are coming out of CMU, and they've got this kind of push to try and make kind of Whisper-like models, which are publicly available with publicly declared training data. And we should probably switch to using those.
Yeah.
Thank
So
you.
regarding Whisper, I think we have the problem. We don't know if they use the evaluation data set in their training. So because of that unknown, probably it's not should be used for the training. As long as they use only the public training splits of the data sets, it's okay. But we don't know if it's using Whisper, the test split from MuseDB 18 or Jamendo lyrics, or all the evaluations. I wouldn't say we can use it for training.
So I think from a team, I think it's sounding like that maybe this Awesome might be the solution. I think as a team, what we'll do is we'll go and have a look at them, see what it's trained on, double check there wasn't any issues here, and then we'll put something on the web and also on the Google group to sort of confirm what we decide is the best kind of approach here. But this is great to sort of kind of raise these questions, because I don't know how you're tending to use this, but the more innovative approaches to using this stuff is great. So we'd like to encourage it if we can possibly make it work. Listen, Paul. Oh, no, Christoph. Sorry, I said your surname there. Do you want to unmute and ask your questions?
Yes, thanks for the introduction. I have just a question about the Whisper ASR. How robust is it to like more lyric produced singing techniques? Because is it really robust if you have more lyric or classical singing technique?
So we have compared it. So there was a paper by Ibrahim, if I remember rightly, which looked at lyric intelligibility in a listening test, and we reran that listening test with a set of people with hearing loss, and then we also did the whisper to have a look at it, and it is correlated. I don't know if Gerardo, you're going to show the graph or whether you can put it in the chat. I mean, it's not perfect. All these objective metrics are not perfect, but it is correlated reasonably well. Gerardo, do you have any more you want to comment on that?
So I will show the graph with Whisper against Ibrahim.
I'll stop sharing if you just want to share it for people to see.
And it's independent. Oh, sorry. Is it independent from music style? So.
Well, these are all pop rock. Well, Ibrahim was a bit more broader than that. But the Muse DB18 isn't that broader data set. But Ibrahim had a mixture. Bill might remember what the mixture is, but it had classical and jazz and other stuff.
Okay, thanks. Yeah.
So it's the best we could find at the moment. So obviously, score lyrics intelligibility is quite new. So there is no a robust metric yet. So
yeah, okay.
That's human performance along the bottom. So that's percentage of word, no, or fraction of words correct. And this, I presume, was our hearing loss panel or Gerardo. And then this is whisper.
Yeah.
So it's obviously is correlated. And Bill has put in the chat the genres that were being used.
Yeah, but there's like an offset, so you need to have a certain intelligibility for human to start seeing the correlation, because there is like a flow effect for very difficult maybe pieces to be understood. Yeah. So maybe it's on the singing technique, because I guess maybe a human can fill the gaps, but the machine has maybe more difficulties.
There was a paper that a linker, I think, referenced where they looked at intelligibility for different genres, and I can't remember, was it classical had the lowest intelligibility? Do I remember that kind of right? Bill's nodding at me, so I think that it may be I could be wrong here, but it may be the worst stuff is a genre we're not looking at. But I wouldn't like to be sure without taking the Ibrahim data apart and just double checking that.
Mm-hmm. Yeah, I think it's Ekstrom and Borg. Yeah. From 2011 they had, but for normal hearing people, listeners.
Yeah, absolutely. Yeah, that is, and young normal hearing listeners as well, who may be less classical listeners. So yeah, it's a slight bias there as well.
Yeah, thanks.
Okay.
Howard, you've managed to unmute.
Yes, I have. The unmuter inside our little thumbnail picture doesn't work, but the one at the top of the screen does. So that's a step forward for hearing, isn't it, this morning? I'm curious to know a little further down the road. I think that the algorithm is so clever, because I did hear a sample that you put up where I think it was a cello was suddenly brought right forward from the orchestra. And as someone who's involved in sound, I was absolutely astounded by that. It was so effective. But a little further along the road, how does the processing reach the ordinary listener? Does it mean that hearing aids will be redesigned, or will we have multi-channel feeds from broadcasters giving a choice of processing? How will that all work?
So I think there's various options. So modern hearing aids can be connected by Wi-Fi to a variety of systems. So you can broadcast direct to your hearing aid. So if you're looking at something that is, say, broadcast audio, you can bypass having to process it on the hearing aid. You could process it on the TV or whatever you're listening via, and therefore have access to more power than you can have on a hearing aid. So that's kind of option number one, is don't try and do it on a hearing aid where there's limited power and processing availability just because of batteries, essentially. And then do it offline. And for recording, that's very easy to do. You could imagine you could even have it pre-processed on Spotify, that there are hearing ones which have been adjusted already. But there's live listening, and there's a case where you're out and about and you're not, even if it's recorded, you just happen to be out and about listening, and then you do need the hearing aid to do it for those models, you need to get something which doesn't have so much processing power. And there's some interesting stuff coming out of, I think it's Sonovo, I think at the moment, with a DNN on the hearing aid. They were just demonstrating recently at IHCon. Bill was there, who might kind of remember if I've got the right company. Apologies if I've got the wrong company, but I think it was Sonova. But they're smaller models than are being produced here. So you then have to find a way of computationally work with a smaller model. So there's a couple of ways happening.
Okay. I mean, I'm old-fashioned. I listen to CDs on very good loudspeakers, and by and large, the musical experience is okay. But you mentioned, or you displayed a thing about compression. That's generally wrong. It's basic. I know it's been designed for speech in these hearing aids, and it's not adaptive in the way the studio compression would be, with multiple time constants to adjust to the pattern of the music. That just hasn't arrived in my hearing aids anyway. And possibly we've got a bit of a problem in that NHS don't provide the better hearing aids. They provide older, simpler hearing aids, and we have to make do.
So what I would say about the amplification stage, which is shown on all these, and I was talking about the baseline, about what they might do. We've got a relatively gentle amplification stage there compared to what you might have for speech. We've set it so it should work better for music than speech, which is kind of what you'd get out of a music program. But we know that's not ideal. And we want in a future challenge to run something more targeted at the amplification stage. These challenges here are more targeted at how do we split apart music and reprocess it or remix it, partly because we've got to do some more work to work out how to quite pose that amplification task. So that we know that's a kind of outstanding thing for us to look at, but that's probably CAD3.
All right.
Anyway.
And can we look ahead to a day when clinics will start testing below 200? I mean, there's 2 or even 3 octaves of music completely ignored in the standard procedure. And even the equipment they're still buying, the new audiology test equipment, it still stops, maybe at 150 if you're lucky.
Yeah, so I think you're right. So if you looked at the audiograms, I was going to put them back up, but I won't bother just for now. The audiograms are limited for because they're tested for speech really, as well. They're the standard ones, and music goes broader than that. But and people did when they for the first challenge say, why don't you have a broader range of frequencies in the audiogram? It's just they're not available. We just do not have the measured audiograms, and we need a lot of them for machine learning. So I think it would be it would be good to broaden that, but we just don't have the data. So I'm going to carry on. It's a great discussion, but I've got another task to get through, and Gerardo's got tutorials to show. So I just want to keep things moving forward. But thanks for all your questions so far. So I'm just going to look at the second task, which will take a bit shorter because it's some of the stuff I've already talked about. And so this is about rebalancing classical music ensembles. So Howard kind of alluded to this. We got a sort of kind of a mock-up demo where the cello is louder. So imagine you're listening to a string quartet, you're a celloist, and you'd rather like to hear the cello line, and so you turn that up by 3 dB. And we want you to create systems which allow that to happen from the stereo mix. So again, we have a scene generator which basically will produce you stereo music. Let's say, I'll just keep talking on the same one, it's a string quartet. And then it also produces metadata, which will be the gain. So that might say cello plus 6 dB, the others 0 dB. And we want that mute enhancement system to take the music and produce the music where the cello is 6 dB louder based on the stereo. And so this is the enhancement block you'll work on. Again, we will give you the hearing listener characteristics. It's the same as before. It's going to be using audiograms and exactly the same set I talked about before. And in this case, the evaluation is purely objective. We don't have a listening panel for this. We are actually going to work with our listening panel about how they use rebalancing, what they want out of it. So we're running an experiment, but we couldn't quite couple it with this challenge and make both work at the same time. So we're actually running that separately. So this evaluation will be purely objective, and we'll be using HAAQI to do the evaluation. I should say, by the way, that in our evaluation, we're using HAAQI. It is a measure which was developed for, from psychoacoustics. So it's not the fastest, it's not differentiable, it's got sort of kind of issues around it. If you want to run for your system a more standard evaluation metric, which is more suited to machine learning in terms of being differential and faster, that's fine. And then look at how that's behaving with HAAQI. That's a possibility. You could refine that. But in the end, we will be looking our evaluation is that process. So in terms of what we talk about, we're talking about ensembles of 2 to 5 instruments and a mixture of woodwind and strings. So as I said, there's common features. The listener's metadata is exactly the same. The amplification stage is exactly the same. The issue we're talking about causal, non-causal, same sort of comments, so I won't repeat those. And for quality, we're using this HAAQI measure again. So that's the same kind of metric we used before. So let's look at the different bits of it then. So the big problem, and I think possibly why demixing hasn't really looked at classical music before, is the lack of databases. What you really want, because you need the ground truth, is you want a set of classical instruments recorded, isolated, and there's not very many databases of that. Excuse me, I just need a drink for 2 secs. Sorry about that. So what's happened in recent times is we've seen some development of synthesized databases using virtual instruments. So an example of that is Ensemble set, which was published a couple of years ago from QMUL, and that has synthesized string ensembles. Now, we wanted also to do woodwind, so we've in a similar way produced a brand new data set of we call Cadenza woodwind, which is on Zenodo and available, which is synthesized woodwind quartets. Now, the reason we wanted to do that is when we talked to our hearing loss people, it's things like flutes being rather piercing is the kind of some of the issues they sort of kind of cite. So we knew there were issues with woodwinds we wanted to explore as well. So again, we had an interesting discussion around data sets, and please, if you've got other data sets and other pre-trained models you want to use, please do highlight it. We're keen to kind of facilitate what works, but what we don't want is a lot of private large data sets, meaning people trump it just by having access to large private data sets. So the stuff about other data sets, please contact us if you want to use them. They should be public. Augmentation's fine, pre-trained, be careful what models you're using. All that's kind of the same as we had before. In terms of evaluation data, there are a small number of recorded, separated classical instruments, Bach 10 and URMP from Rochester, and we're using those. And again, you mustn't use those or the bits of the evaluation data set that we use to refine your system. These are purely to test what's going on. So we have a synthesized training set. We have real players in the evaluation set. There's obviously a mismatch there, which obviously makes machine learners get very nervous. So we've also provided a small set of real recordings to help you tune your sets. So we've got a small set of real recordings. And that's intended to allow you to look at and just see what this mismatch between synthesized and real recordings is doing for your systems and maybe make adjustments. Now, we know from the people who worked on Ensemble set, they did a paper where they trained on their synthesized data and then they checked it by using real data. So we know the mismatch shouldn't be a disaster, but we wanted to give you some data to work on to help you test that mismatch and whether it's an issue and change your systems if necessary. But a big warning here, this is not a statistically balanced data set. So don't stick it in the learning loop, I would suggest, because we haven't got a balanced data set to give you is the problem. But we're giving you some examples to help you maybe look at that problem of mismatch. So this is the system we're going to look at. I'm just going to talk a little bit about the music enhancement here. So again, you could use a demixer, remixer, and that's what we've done in the baseline approach. And of course, music source separation is a big kind of area of research. But we're also, again, really happy to see other kind of processes as well. That's what we've used, but don't feel that's the only approach that is available. Do what kind of you think is interesting. So here's our baseline, where basically we have music to enhance. This is showing for a trio. So we demix it into 3 instrument blocks. We have these gain targets, which are the sort of turn the cello up 6 dB. Those apply and change the level, and then we just add them back up and remix. And yet again, we have this amplification, same as before, to basically amplify the high frequencies. And then we have the enhanced signal. Just some other rules before I kind of finish on this task. Please pre-register your teams because we're running listening tests. It's really useful to know how many people are going to enter, so we can actually start planning panels, recruit the right number of subjects, and all that. It really helps with us with planning. As I said before, if we're using objective metrics. We also got a listing panel for one of these tasks. If you wish to submit different systems tuned differently, that's fine. We don't want a large number of systems, but a couple of systems, one tuned for objective, one tuned for listing panel is fine. We allow anonymous entries if you come from a company and don't want to say who you exactly are. And it's really important you give us a technical report, and there's details on the website so we can check that you meet the rules is really important for us as well. And the other thing to say, which we didn't have in the last challenges, is we have a prize pot. So this is an IEEE Signal Processing Society challenge officially now, and they've made a prize pot available of $1,000 for the best systems. So thanks to the IEEE as well for that. So do you have any questions on this, on the rebalancing task that you wanted to add about models or data or anything like that? Jump in, Howard.
Yes, I feel from listening so far, I'm doing my very best to comprehend. I think anything ahead is going to be a little bit more layperson friendly. There are quite a lot of technical terms here, and I have to stop and think. I wrote several down. I'm not going to bother asking you now, of course not. But a bit more accessible, I think, is going to help that process if you want people other than really clever scholars to respond to you, you know?
Yeah, well, maybe we've missold this webinar a bit because it was aimed for entrants, so it's aimed for signal processors really. So it's great you've come along, Howard, and maybe we should do something public facing, but or more layperson facing. But this was designed for people who are doing the signal processing tasks to ask questions. So yeah, I'm sorry we're getting quite technical, but that's the reason we're getting quite technical. And I warn you, the next bit will get even more technical because we're going to start showing software and stuff. So you're
It's
right.
good to see good brains working on these things. Quite happy about that.
Yeah. But we are talking, and we have talked to people about doing some more sort of public facing stuff, and we will be doing more going forward. We're just our concentration early on has been getting these challenges up and running.
Sure. Great. Thank you.
Do you have any questions from the rest of the audience about that particular tasks? Again, you can type them in the chat. Someone asks if this is being recorded. Yes, it is. It'll go up on the website. I don't know if it'll happen today. It might happen next week, given all that's going on. If there are no questions, there'll be more chance
there is
to.
One here. This is going to be irritating, but I expect you can answer it very quickly. I couldn't work out what causal or non-causal processing actually meant.
Oh, right. Okay. So in signal processing, can you look into the future? Are you Mystic Meg, essentially? So on the hearing aid, you can obviously only work with what's going on in the past, and that's called causal processing. So all you can do is know what you've heard already. Non-causal is where you look into the future, and that can be an advantage in music processing because you can see the whole piece and make decisions about what to do at this time, knowing that, for example, the whole orchestra is coming in a moment, which you can't do on a hearing aid, but you can do on recorded music.
Lovely. Thank you. Good.
Okay. Oh, sorry, muted myself there. If there's no more questions, I'm going to pass over to Gerardo, who's going to take you through some tutorial work and look at the sort of kind of different baselines. If you've got questions, you go through, feel free to use the chat and etc. But over to you, Gerardo.
Thank you, Trevor. So now on the website, if I can try to share that. I don't know if it's sharing. No, it's not sharing. I can share, doesn't matter. There you go.
Yeah, that's coming through now. It's thinking about it.
Yeah, it's taking ages.
Yeah, I can see the PowerPoint at the moment.
Yeah, brilliant. Thank you. So now on our website, so on the top menu, we have this new option, tutorials, where basically we'll open a new website constructed using Jupyter Books, for those who know what it is. but basically it's a static website with some of the tutorial. Was constructed in that way so you can run the Jupyter notebooks, download it and run the code locally. And you can open an issue in the GitHub so you can propose new tutorials or report some errors in the tutorial. So in that way, we can keep all this updated and helpful for everybody. So now you should be looking the website. So I'm gonna try to go. So what we have currently is some generic use of the code. So how the metrics in the Cadenza 2 are running, or how they run, and some details in the challenges. If there's some part you prefer me to take more time, just you can interrupt me and let me know. I'm not gonna show, but in the tutorials I will start adding some videos with the time, so it's not just plain text. But I'm not gonna show the videos now, obviously. So the code, for everybody to know, is on GitHub. And we have organized the versions of the code to match each release of the challenges. So currently, Cadenza 2 is the version 061. The ICAS 1 was 041, and the Cadenza 1 was 034. So we are doing this, so if you want to run in the future a challenge and you want to run the stable code at that time, it's better if you download and then check out the proper version. Even though the main branch will have the code, we don't keep testing if the code is not broken. There's some tests, but we can only ensure at this moment that the tag version is the one that everybody ran when the challenge was live. So in going into the metrics, so as Trevor said before, we have the audio quality, which is using HAAQI, and the lyrics intelligibility, which is the correctness transcription. So in terms of HAAQI, as Trevor said, this is an intrusive metric that requires a process and reference signal, and it compares both signals. So HAAQI amplifies the reference and expected the process signal have the same amplification. So in the previous challenges, that amplification was nullar, but now in our case, we're using a multiband dynamic range compressor. So it is important if you want to optimize HAAQI that the amplification is the same for both. But if you think that the amplification used for the reference is not the optimal for the listener panel, as Trevor mentioned, you can try another amplification, but mind that it will affect the HAAQI score. So to run HAAQI, you have the module storing clarity evaluator HAAQI.py. And basically, you need the process signal, the reference signal, the sample rate of both, what is the audiogram of the listener, the equalization, which is a parameter that indicates if the reference already has the amplification applied to it or not. And level 1 is the reference level of the it's the level of the reference signal where RMS equal 1. So to use the multiband compressor amplification, here in the tutorial, I'm using a sample from Librosa. So basically, I'm setting some in the tutorial a seed because HAAQI has some random noise applied to the signal system part. So we do this in the evaluation of the challenges as well. So to seed this NumPy, so everybody has the same randomness. We create an audiogram using this audiogram class, and we construct a multiband compressor. So the compressor, I will show it later in detail, but basically it needs what are the crossover frequencies, the sample rate of the signal, and the details of each compressor. So if we have, in this case, 5 crossover frequencies, means we are generating 6 bands. So that splits basically at these frequencies. So we need parameters for 6 compressors. And then we can compress the signal to the reference signals. And in this case, the process signal will be the same as the reference. So basically, will be the max HAAQI we can get. So the reference is equal to the process in this case. HAAQI operates at 24 kilohertz. So in general, inside HAAQI, there's a downsampling, but I found that it's always better and more clear if we do the downsampling when calling the HAAQI. So in Clarity, we have a resample function you can use, or you can use a personal one if you want. But in the evaluation, we will be doing this in the evaluation code. So in that way, both signals enter with the same sample rate. Equalization is equal to 2, which means the reference already have the amplification applied. That was we did here. And the HAAQI score is almost 1, but not exactly 1. So I hope you can hear this reference. But with the amplification using the multiband compressor. So I hope you were able to hear the differences. Those are given by the level thresholds that are indicated in the audiogram. So at the different frequency bands, center frequencies, basically, you have this lost in decibels. So the amplification attempt to recover that. So HAAQI can operate with different amplification. Yes, it can. That's what we did in the previous challenges using Nalar. If you want to explore Nalar, well, you can go and run the rest of the this tutorial. And at the end, there's a comparison between the reference, the amplification, and using Nalar. In this case, Nush. You can later decide how similar or how different they sound, the different amplifications. For the word correctness, for the lyrics intelligibility, the correctness basically is computed as the number of corrected words over the total words in the sentence. So I showed you before, using the Ibrahim data, we have a correlation of 0.69, and the x-axis, the human performance, the y-axis is the whisper correctness. So there's a reasonable correlation, but obviously this is not perfect. So if we can come out later after the challenge with a better metric, so we can keep using in the future, will be great. And if you have some proposals thinking in the scope of the challenge, which is pop rock music, we will be happy to hear it. So, well, to compute the correctness in Cadenza, we can take a sample from one of the audios from Ibrahim, which is an excerpt from Aretha Franklin's As Long As You Dare. The lyrics was annotated as long as you hold my hand. That's the reference. I think it's important to mention here that this score is with the background. It's not an accompaniment singing. It's singing with the background accompaniment. So there's a masking effect from the instrumentation as well.
As long as you hold my hand.
From Aretha. So, well, as I mentioned in the chat before, we are using the base N model from Whisper. And we can do the transcription from the normal signals, and long as you hold my hand is very close to the reference. So it has an error in the first word. But then we use GIWare to compute the measures, and we use the hits over the hits plus substitution plus deletions, so over the total. So we have roughly 0.85. That is in normal for in normal conditions, but we are using as Trevor mentioned, we are amplifying the signals. So again, we use the multiband compressor. And we compress the left and right side in the separately, because the audiograms or the hearing thresholds are not the same in both ears for almost all the people. So the amplification is independent for side. And then we apply a hearing loss simulation using the MSGP implementation in Clarity to simulate the listener's ear. And these are the signals we pass through the Whisper. In this case, also we pass the left and the right signals separately. And the score we save is the better ear. So as you can say in this case, and you can see in this case, the left ear got a 0.85, but the right ear get a 0.43. So the score we are saving or keeping is the better ear. In terms of the HAAQI, I didn't mention that before, we are doing an average of left and right. So this multiband dynamic range compressor we implemented we have implemented in the Cadenza code is based on using Linguist-Riley crossover filters, so we can split in the different bands the signal. This crossover filters, you can find it in Clarity Enhancer, multiband compressor crossover. So you can use these filters not only for the challenge. If you need to use a all-pass filter, which can work with any number of filters. But in order for, you're more than happy to use it. So the crossovers, you need to specify what are the crossover frequencies, and then just filter the signal. So for example, this random signal, mono signal of 1,000 samples is filtered into 2 bands with a crossover frequency of 8,000. You can plot and see how this crossover filter or what this crossover filter is doing. So we'll generate a low pass and then a high pass filter. When you add those filters, you have a zero response, which is the idea of these crossover filters, or all pass. Or you can request for more than one crossover. In that case, you also will have, well, the low pass, the high pass, but you will have a band pass in the middle with an intersection in the crossover frequencies. For our compressor, we are using an implementation from a compressor from Demetrius, the Queen Mary University. And the compressor needs a threshold ratio, the compression, and attack, release, makeup, gain, the knee width, and the sample rate. So you can compress a signal with these values, and you can see how they're decompressed. The multi-mag dynamic compressor now integrates both the stages. So as I showed you before, you need to specify what are the crossover frequencies and what are the parameters for each compressor. So these parameters are saved into this dictionary. If you have a single value, that means the same for all the compressors. If you want different values for the different compressors, you need to specify the list. And after running the compressor, well, you have this compressed signal. And as Trevor said, well, we need to normalize the signal before the compressor. So you can do a loop normalization. And this is basically how we do it in the challenge. So each challenge, both task, operates in the same way. You will download some audio tracks and the metadata. In general, all the challenges have these listener dictionaries. Some dictionaries, in our case of the music we are processing. So the listeners, the structure is we have a listener ID, the center frequencies, and the audiogram for the left and right ear. So we will have listeners for the training, a different set for the validation, and a different set for the evaluation. In this case, with this demo data, the music is just showing the name of the track, and this is from MuseDB18 dataset. The baselines for our challenges make use of the Hydra and submitted technologies, so you can, for the configuration, for parameters, and run it in HPC environments or local environments. So we have in all the baselines a config.yaml file, and the structures are very similar. So we have a path section where I specify the path where the dataset is located, and inside that, where is the metadata, or what is the path for the metadata, the path for the audio samples, and then the path for independent or specific metadata files. The last path you will find is the experiment folder. This is where all the results of the experiment will be stored. Then you will find the sample rates where we operate. So the first usually is the sample rate from the original audio. Then the sample rate for, if we are, this was for the Cadenza 1 sample, so the stems were stored in 24K, so we're using without downsampling into HAAQI. And for the remix, which is the output signal that will be presented to the listener panel. Then you have some parameters for the amplification. In Cadenza 1 was for the NALR, and some specific parameter for the evaluation. You can read more in the Hydra documentation by using the CLI environment. You can override different parameters just using dot. Make it very easy to explore different parameterization. There's any question at this point before going directly to the baselines?
Just to say, Gerardo,
Yeah.
excuse me. So there's a couple of questions gone on the chat, and thanks for asking them. I've answered, but there was one which you might know the answer to. So there seems to be a small number of sources in the task 2 where there's 6 sources, and I thought we were going up to 5. Is the question. And I wonder if you knew about that. I noticed 3 pieces in the train split have 6 sources, but the corresponding scenes only have 5 gains.
So
I'll put it in the chat again. It's the bottom point.
yeah, thank you. So I noticed 3 pieces in the train split have 6 sources. Oh, thank you for that. No, it should be 5. We can check that to probably to see what are the details of those.
It sounds like
noticing.
Yeah, some of the data sets we're using have got more instruments, so it just looks like it's a mistake. So we'll have to just double check. It's obviously only a small number of pieces, so apologies for that.
Yeah, if you can send that later, it will, which are the IDs of the track, that will be help us to quickly find it and see what we can do with those. But definitely we can find a way to.
Yeah, I mean, you could just draw on the tracks.
Yeah.
So, as it's only 3 out of the whole lot, it's not going to, and it's in the train set, it's not going to create any disasters. There was another one, I don't know if you, there's an interesting question. I'd be interested to know if other people have got an answer to as well. So again, it was Austin asking about using non-classical music for task 2 in training. So you could imagine, I mean, it's not what it's suggesting, but we could start off with a demixing model which has been trained on Muse DB18 HQ, got the right way around, and then retrain it for classical. To me, that sounds perfectly fine because it's all public domain, but I don't think our rules necessarily explicitly allow for that.
Yeah, I don't, as long as they public data and they think they can help, I don't think there will be a problem. They will find some mismatch in the kind of music, but definitely there's some match between them.
Okay, we've got a list of the music. So yeah, I think what I kind of answered in those chat, for those maybe some people can't see the chat, but there's been some questions about pre-trained models. Is essentially, I've given up my brief thoughts and I've taken a note of the question, as a team, we'll go away. We'll just double check we're happy with it, and then we'll put something definitive on the website and something definitive on the Google group. So we're not, we'll just think. I can't see why we can't allow that. But let us, and as a whole team, think about it in case there's something we haven't thought off the top of our heads. Were there other questions about what Gerardo was just shown? So that was kind of going back slightly in time.
Yeah. Share it again then.
Yeah, I hesitate to ask things which come very much from my position in sound recording, but compression is the great black art. And if I see a compression specification as 10 milliseconds attack, or even one that I wrote down from 50 milliseconds, I say, what's that going to do to music? In the era of look ahead, where we don't tolerate overshoot, what is that going to do to music? Has that been part of the discussion to assume a certain attack and release speed? And the release speed also, as I wrote down, of 100 milliseconds is very suitable for some speech, but again, absolutely destructive of music. Sorry.
The best part of the reason to run these challenges is, I'm going to throw to you in a moment, Bill, just to make you worry. The whole point of running these challenges is we want to move away from doing this sort of compression. But as I said, these challenges are focusing on other parts of the chain, and the application is therefore kind of taken for, what practice we currently have, but we're not saying it's ideal. Bill, did you want to comment actually on the specific attack and release times? Because I think you were the one who would. I'm not a hearing aid expert.
I don't know.
I'll just throw you under the bus. Can I throw you under
it's-
the bus, Bill?
Oh, well, you could definitely always do that. Yeah, exactly. The bus can roll right over me, as long as it gets somewhere on time. No, Howard's point is absolutely apt that when it comes to music, and then also the type of music, has that music already been compressed, and how much has it been compressed? But you're absolutely right. Hearing aids, and this is part of the project, is the fact that hearing aids are tuned for speech. And the studies have shown that generally a longer release time is better for music listening and things like that. But here we've just wanted to, we need, as Trevor said, we're fixing that part of it and then looking at this other component of the processing that might not actually be something that the hearing aid does, but someone in a production studio could do to the music. Back to your question about what's causal and non-causal. So all these sorts of non-causal solutions that somebody could remix it for. And then we just have a, albeit very generic, hearing aid. And granted, it is a bit fast on the compression times, but they're very mild. And so the idea is what it's doing is just doing a compensation so the person can hear what's going on. So we just don't have that sort of nagging, is it even audible? So we get past that and then we sort things out. But you're absolutely right. And as we continue this project, that just keeps coming up and up again. Is it's like, how do we handle the loudness for those who suddenly have all these challenges that Alinka was talking about earlier? But thanks for that. Yeah, it's a really important point.
Yeah, I'm gonna continue.
Yeah, good idea.
One of the time that
You've got about half an hour, just to warn you. I mean, you can keep going, but just to let you know, rough timing.
Yeah, for the lyrics intelligibility baseline. So first, it's important to use the tag version v6, version 061. So you can clone the recipe branch to 061, and you will have the last the version for this challenge. We also prepare so you can explore a little bit if you want to start with little data. We prepare a demo data for the Cadenza 2. So this data is just containing 2 audio samples from the validation, extracted from the validation set, and 2 listeners extracted from the validation set. So in the config.yaml of this challenge specifically, you will find a path you have to, you don't need to change this path, but it's the path to the alpha files, which is the same set of alphas for all the splits, for all training, development, and evaluation. But you will need to change the music, the music file, the listener files. Well, basically all the ones that set valid here for the set you're processing. So be careful to call the scenes listener for this valid or for the train, as well the scenes for the train, the compressor parameter for the train. Otherwise, you will get an error when running. So we are having, we have 3 sample rates. For the input is 44.1 kilohertz. The remix and the signal you will submit is also 44.1. This basically because the hearing loss model we have, MSGB, operates in 44.1. So if we request lower sample rate, we will need to upsampling the signals, and that could add some distortion, unfair distortion to your signal. So we prefer to request the signal and then we can do a downsampling when running HAAQI. But the hearing loss will use your input signal, or you submit a signal. In the separator, part of the YAML file, we specify the causality we're running. That indicates which model we will use, or which pretrained model we have, we will use. And because it's task 1, these have the number of sources of 2, accompaniment, or lyrics. The next segment overlap are basically parameters used for the separation. When I have a long track, we do split and overlap. The enhancer part of the YAML file specify parameters for the compressor that are common for all the listeners, which is the crossover frequencies, the attack and release values, and the thresholds. And in the evaluate, well, here we specify which whisper model we are using. If we are setting the random seed I showed you before, this is a parameter we use in the hearing loss simulator. So now what we understand we are clear what are the parameters in the YAML file, or the parameter to run our baseline. We can run the baseline. So the enhancement part is in the enhance.py script. So this, I'm not showing the top part of the script because basically what I'm doing is loading the different metadata files, which are JSON files. Then using the causality parameter, load the causal and non-causal models using the load separation model. This function basically downloads our pre-trained model from Hugging Face. It creates an instance of the multiband compressor and loads all the scenes and listeners from the metadata, and then start processing one scene listener at a time. So for each scene listener, we load the track for that scene. And what are the segment of that scenes where we will process? We normalize to minus dB loops. We use the separation, the causal or non-causal, depending on the scenario we're running. We separate the vocals and the accompaniment. And we do the down mix using this alpha function as a beta for our down mix signal. So this method, if you want to explore different ways if you just want to explore different ways to downmix the signal to stereo again, you can modify this function as well, keeping the rest untouched, and you will have a different new mixture for the alpha. Then we apply the amplification to our enhanced signal using the multiband compressor. And the signals are saved into a FLAC format using the sample rate indicated in the YAML file. So if you are in shells running on shell, you can call the enhance.py script. And if you are going to use the same dollar curly brackets Hydra kind of way to use the to connect the different path, you need to add these brackets in the beginning, simple brackets at the beginning in each of these parameters. In that way, that will be this dollar will be interpreted by Hydra and not by the shell. So here we processed these two listener, and each listener for these two scene, and each scene was one listen only. And you can see we saved the track using the scene ID, the listener ID, and the alpha value in the remix. So later, you can listen the signals, however they were the outputs. In the evaluation, you have a lot of more output, and this is basically all the output from the hearing loss simulation. So for our scene, we process the hearing loss before getting the scores. This evaluation process, after completion, you will find inside this path X folder scores CSV file with details of the scene, the song, the listener, how were the HAAQIs. This was modified now in the last version, so you can have the transcription from the left and right as well, not just the scores. So that will, in a way, to help. That was modified to get the transcriptions and the reference, so you can compare what is happening in the Whisper as well, using just this file. Otherwise, that information is lost if we don't save it. That is the first task. I can stop here. Is there any question in this code where I explain it, or I can continue to the next task?
Yeah, give people a moment, because I think questions sometimes take a bit, excuse me, a moment to emerge.
Yeah.
It appears not.
Yeah, I think I can show the rest. So in the rebalancing classical ensemble, this works in a very similar way. So we're using the same tag version because it's related to the challenge in total, not each task. So both tasks are in the same tag. We also included this specific data for this challenge, so you can demo for it. Something I didn't mention before, but when you download the demo, you will download data for both tasks, and they are separated into After uncompressed, you will have get a folder Cadenza data demo, Cadenza 2 or CAD2, and then a folder for task 1 and a folder for task 2. And as you can see, both will have an audio and metadata subdirectory. Here, the parameters are very similar, but unlike the previous one, we have here gains instead of alphas. These are the gains metadata, that general gains that are then specify which one are we using inside the scenes. Here, unlike in the previous one, or in the task 1, the remix we are requesting is just 32 kilohertz, because we don't need, in this case, the 44.1 kilohertz signal. The separator parameters are very similar. We also specify the causality, but we also have a residual parameter that we use after separation, separate the signal. So I can show you later better. But basically, the important ones are the force redownload, if we want to redownload the model or not. When we call in HAAQI phase, this add residual is a value between 0 and 1, which indicates how much from the other instruments we want to add back to the separated or schematic instrument. This to recover some information that may be lost in the separation. The causality on, again, this separation process. In the task 2, we train an independent model per instrument. So here, each model is also separate 2 sources. So our target instrument, for example, we have a model for a flute, a model for a viola, model for the violin. So for each model, we have 2 sources, the instruments and the rest. So this residual will take a percentage from the rest and add it back to the target in case there's to reduce some distortion due to errors in the separation. Again, we have the enhancer, so the parameter for the multiband compressor, and the evaluation process. In the enhance, here is a little bit more simple. So we again, we load all the metadata, we load all the models in advance, all the causal and non-causal models. So the 1 model per instruments. We create our multiband compressor instance, and then we process 1 scene listener at a time. We define the parameters for the enhancer. We look what are the instruments that are composing the mixture. So I don't know if this was clear before, but the different ensembles have different number of instruments out of a pool of, if I'm not mistaken, 9 instruments. The knowledge of what are instruments composing the ensemble or containing the ensemble are known and is part of the metadata, so you can make use of that. And that is what we are using here. So we are reading this metadata and getting the list of instruments. So this is helpful to, so we use a specific model and not, or the correct models to separate the target instruments. We read the mixture signal. These are all in FLAC format. So this to reduce the package size, basically. And we extract the segment we are processing. So then we estimate or decompose the signal into target instruments. So we call the function decompose signal. So in this case, we pass all the models, the mixture, what are the sample rate, in which device we're working on, CPU or CUDA, what are the source, what are the instruments in the mixture, what are the listener, and the residual percentage. And that will return the stems, or each individual instrument, separated instrument. So some of the ensembles may have two voices or two interpretations or two parts of the same instruments. So the baseline is not dealing with that. So the baseline is not dealing what happened with there's a violin 1 or violin 2 in the same mixture. So what it's doing, the baseline, is separating the violins and then getting average gain for those. So for example, if the original mixture have a violin 1, violin 10, and a viola, the baseline will separate the violins, will compute what is the average gain for the both violins, and apply that gain basically to the violin. If you can train a model that can tackle that kind of scenario in a better way, that definitely will result in a better output. So after we have this new gain, so the gain sync, that's this check repeated sources is doing. It's looking for this average. So now we can apply the gains to the stems and do a remix of the stems, adding it together. We again adjust the level or normalize to minus 40 dB. And processing the remix for listener, basically apply the multiband compressor to save it finally in a FLAC format. So after running this, so you can see, well, the system will first download the different models. So we have a non-causal for bassoon, for cello, clarinet, flute, oboe, sax, violin, and viola. And then we will process the signals. Here, again, we process it two signals for, or two scenes for two speakers, listeners, sorry. And the evaluation will only compute a HAAQI. Here, we don't need a hearing loss simulation, so you can see the output is more concise. And the scores files output, the output score files will give you the left, right HAAQIs and the average HAAQI. And that complete my presentation of the different tutorials. So I'm happy if you raise an issue in the GitHub, indicate if there's something not clear, something that was wrong in the tutorial, or you want me to expand on something or write a new one. So please do if you have an idea. Thank you.
Yeah, thank you, HAAQI. Just to say that's linked off our website now. So if you wanted to go back and have a look at them and go through them in detail, oh, got a nice round of applause there. Please, yeah, and you know, the part of this project is trying to support the community to work on these problems. So if you think there's a tutorial we're missing or it's not clear, please feel free just to get in contact with us. We won't be offended. We'll be very happy to try and see if we can make it better. I wonder if there was any last questions that people wanted to ask about the challenge. Go on, Howard.
That was all mostly incomprehensible to me. I'm simply not trained in that kind of language at all. But I'm experienced in audio, and excited to think where this is going to ultimately lead, and whether you'll be getting onto hearing aid manufacturers to look at those terrible limitations that they're still building into their aids, whether you'll educate them to do things better, and what sort of dialogue you may have with broadcasters as well, so that they may use that metadata you talked about to give us those choices in real time. Does that make sense?
Makes perfect sense. So we have a set of project partners who I haven't actually acknowledged today, who are people from industry who sit on our steering board. So we have BBC R&D is one of our project partners. And in fact, we've done active work with BBC R&D on speech intelligibility work, something that's just been going on recently with colleagues at Salford. So that's something definitely linked in, and they haven't really implemented anything with Call Out the Music yet because we're still in the process of developing the research. In terms of hearing aid manufacturers, well, we go and present at conferences like the virtual conference on computational audiology and the World Forum on Audiology, which just been about where hearing aid manufacturers are on the project. But we also have on our steering board, we also have one hearing aid manufacturer as well. So we do have direct links. I'm not the best person linked in, for example, Bill Whitmore would be better linked into them. Yeah, so we do have good connections with them, and we will be using them.
Excellent, good news.
So if there's no more questions, I think I'll wrap up, because it's been nearly 2 hours, and I know how tiring. It's slightly easier for presenting, I think, but if you're just listening, it's a long time to just listen. So thank you very much for your time today. As I said, the message here is we're here to help. So I've taken away some questions that we're going, as a team, going to look at, and then we'll put something on the Google group and on the website for whatever way we think is correct. But if you've got any other questions or things we can help with, just please feel free, either the Google group or find the email address for the Cadenza Challenges project and drop us an email. We'd be very delighted to try and see what we can do. But otherwise, have a good rest of Friday and enjoy your weekend.